Alright, so here's a slightly more formal way of looking at the bell work problem and the problem from yesterday. So we want to find the area between, in this case, the x-axis and then the vertical lines into the curve. So one way that you could do it is you could divide it into only two intervals. Okay, if you did that, then you can find the length from U1 to U2 and from U2 to B. That would be, I guess, either the length, the width, or the base, whatever you want to call that. And then you could find out the height of the function by plugging in the value that you have for U and finding the function value. So does everybody see how you should be able to find both parts here? Like this point can be found by evaluating the function at U. This point here can be found by evaluating the function at U2. You know what the locations are here, here, and here. So you can find that you can find the distance. Okay, basically that's b minus a over 2. So that will give you a length here and a height here. So the area here would be length times height. You do that here, length times height. You add them together and you have an area. Okay. You think this is a good estimate? No? How can you fix it? Make more boxes. This one would be better, wouldn't it? Okay, so here we divided it into 4. Then you go through the whole process again. Okay, and you find the areas and you add them all together. Now, I don't know if you guys noticed one thing here. One other thing is, look where the location of the dots are. So, U1 is to the right of A, right? Yes? Here, U1 is on A. So one of these calls is called a left endpoint. That would be this. Here we're using the left endpoint of our intervals on the x-axis. So we're using this point here and then this y, and we're making our box from there. So your first box is going to be here, and then you use the left endpoint for your second box. And if you keep making more boxes, you just end up doing that more often. Over here, do you notice that after we divided into 4, we took the right endpoint and we went up and we found this area, and then we took the right endpoint up and found this area, and the right endpoint and the right endpoint. You guys okay with all that? There has to be a difference right between the left and the right endpoint here, and I can show you here. If you had used left endpoints, you would be using this one here and this one here. Do you see that? And then this would have been a height, so you still would have ended up with this. And then this would have been a height, so you actually would have been over here. And then this one here would be a height, so you end up over here. So if I sort of mark these, so here is another estimate that we could have found for the area here. And this would then be, I don't know, would it be more or less accurate? On this case, I'm not really sure. Which one do you think is better? The one that was in gray or the one that I sort of striped? Anybody? Huh? You think they're about the same? I think so too. Okay, so where yesterday, maybe when we did it in class, there was one that was definitely better than the other. If you have a curve that's somewhat, I can't say it's irregular, but you know, it goes up and down in different spots, it's really hard to see if the left or the right endpoint one would be better. Right? So, you know, in this case, for example, I don't think it's real clear to see which one would have been better in terms of your estimate for the area. They're both a little bit off. Okay? So, the whole thing about averaging, that what we did yesterday, because yesterday the curve was continually increasing, right? Like when we did the one yesterday in class, we had a graph that looked like this, and the whole graph was increasing, so the left and the right could be averaged easily, and we ended up with a point or with an estimate that was pretty good, because we took the one that was too small, averaged it with the one that was clearly too large, and that works. But that doesn't work if you have curvatures like the one I have over here. Okay, so the whole averaging bit that I mentioned yesterday, that's not what we do. what we just do is, how do you get a better estimate? We went from 2 to 4, so probably a better estimate could be found by using maybe 8, 16, and that's the part where the limit comes in. Okay, the limit ends up being making these rectangles smaller and smaller and smaller. Okay, so here's your question, and it's split out into parts on the following couple things. So it's fairly straightforward once you see it, hopefully. So approximate the area under the graph of 2x from 0 to 1 by partitioning the 0 to 1 into 2 subintervals of equal length and choosing u as the left endpoint. Okay. Now unfortunately they did a bunch of this already for you. So if we go from 0 to 1, so you would do 1 minus 0 divided by 2 is a half. That's why they put a dot at a half, because we now divided it into 2 intervals. Okay, I'm going to leave this one open. Picking the left endpoint means that this is my first area. So from 0 to a half, okay, and then the function value at 0. So that's why f of 0 is here. So area 1, in this case, would have been from 0 to a half, so the distance here, which is, what's this length? That's 1/2. I know this is obvious, but it will get more difficult at some point. And then we're going to multiply by the function value at 0. Well, what's the function worth at 0? 0. And you can already see that, so that's why you have 0. Then you take your second endpoint, which is at a half, right? The distance from a half to 1 better be a half again, right? So area 2 here is still that base of a half, and now you take the function value that you have when you plug in a half into the function. So what do you get when you plug in a half into f of x is 2x? You get a 1. So a half times 1 is 1/2. Add those two together. So right now my estimate is 1/2. That's not a very good estimate. We okay with that? I'm going to do this again. I want you to see the difference between left and right endpoints here. This would be exactly the same as I just did a moment ago. So we divided it into 2 parts again. Each of the parts is a half long in the base, but now you can see these are already colored in. So if I do this similar to the other one, that would have been open. I'm using the right endpoint. So I'm going to go up to the right endpoint and evaluate here. Okay, so maybe I should have, so area 1 would be the base, which is a half, times the function's value at a half. Well, fortunately we already know what the function value is at a half from the previous one. That was a half, right? Okay, and a half times a half is? It's 1/4. Sorry, I need the function at a half. It wasn't a half there, was it? When you plugged in a half, what was the function value? It was 1. I'm sorry. Right. And a half times 1 is a half. Okay, area 2 would be that base, which is still a half. And then evaluate this function at 1. And when you evaluate the function at 1, you get 2, and a half times 2 is 1. So my best estimate right now would be 1.5 for my area, which is not a very good estimate. So Andrew, how can I make it better? Follow along.
Make the subintervals smaller.
Okay, make them smaller. What happens if you divided it into 4 parts?
More accurate.
It should be more accurate, right? So now your subintervals, the length of the subinterval will be 1 minus 0 divided by 4, so each one of these should be 1/4. So the base every time is 1/4. And then I'm going to do the same thing. I have an area here, I have an area here, one here, and one there. So we're going to go a little bit faster now. So how do you find the area? It would be, what do you need to do with all those four? The total area would be the, how do I find the total area? Yeah, but so I find area 1, 2, 3, and 4. What do I do with them? Add them together. Thank you. You were already ahead of me. And each one of these is base times height, right? What's the base for every one of these? 1/4. So you can start seeing some patterns here, right? And then for the first one we need f of 0, right? Left endpoint, f0. Then we do 1/4 times the function value at, let's see, we're 1/4 of the way. And then I do 1/4 times the function value at a half. And I do 1/4 times the function value at 3/4 because we're using left endpoints. So I don't quite make it to 1 because the last endpoint will be at 3/4. And then you figure out what each one of these is. So that's 0. What's the function worth at 1/4? It's 1/2, right? Look, 2 times 1/4. Keep in mind that that's the original function. So that's a half, right? Yes? And at a half, this thing is worth 1. And at 3/4, this thing is worth?
2.
Not 2. 2 times 3/4. 3/2. And then when you add all this, you get 0.75. So that's the left endpoint 1. Are you guys okay with this? I'm going to go a little bit faster than on the next one. I just want you to see the notation at this point. Okay. Same story. Now what am I using? Not left endpoints, but right endpoints. Base still a 1/4 for each one of these. So now it's 1/4 times f sub 1/4, right? Yes? And then the next one would be at a half. And then the next one would be at 3/4. And then the last one would be at 1, right? Focus on this part for just a second. Where have we seen that before? Haven't we seen exactly that part in the other one? Okay, I'm going to go back for just a second. Isn't that the end over here? And this is why I wanted to show you the notation again, to be honest. Isn't this thing, these three, aren't they part of the next one as well? 1/4 times 1/4, 1/4 times a half, 1/4 times the function of 3/4. That's the start there, right? So the only difference is the left and the right endpoint part. What do you think that implies if you keep making these things smaller and smaller? What's going to happen? I agree with that. That's fine. Kyle said if I keep making the base smaller and smaller, so let's say I make the base 1/100. Which 2 points are going to be different? The first and the? But 99 out of the 100 are going to be exactly the same, right? Don't you think that the left endpoint and the right endpoint end up being basically the same thing if you keep making them smaller and smaller? Anybody? Would you agree with that statement? If I keep making them smaller and smaller. So if I shrink this, if I make this tinier and tinier and tinier, don't you think that basically I get a huge chunk of information that's the same for left and right? I get one number here on the left, and I get one number here on the right that's different. And you think that those two are going to make a difference at all in the overall sum? Do you really think that 1 out of 100 is going to change the overall sum? Keeping in mind that you have an area now that is going to be determined by a curve, and you have sliced it like this, with that being like basically nothing. So that's like 1/100th of a unit, and you're going to do 1/100 times some height. Do you really get much out of that? Don't you think that that will be basically the same thing as I did it over here? So left endpoint and right endpoint, if you do this more and more and more, and basically you get the same thing. Okay, well that's, what do you call that when you make it smaller and smaller? That's what we've been working on this whole chapter. That's called a limit. By taking the limit, the left and the right estimate basically end up being the same. So we have a fancy name for that. It's called an integral. It just means make your endpoints, make your intervals smaller and smaller and smaller, repeat the whole process until you can't make them any smaller, and your left and your right will be the same. That's finding the limit. Okay, so this is what it's sort of trying to show you over here, that if you use left versus right, do you see how the numbers converge? So the example that I did with 100, or that I asked you about with 100, this would be the estimate if you used 100 subintervals. This one gives you 0.999, or 0.99, sorry, and that one gives you 1.01. Is that a significant difference? No. And if you still think it's a significant difference, which, you know, somewhat a matter of opinion, then my suggestion would have been, well, then let's just do this with 1,000 subintervals. See what happens to that difference. Where do these end up going, by the way? Yeah, the limit for, we'll just say the left of this area goes to 1, and the limit for the right for this area goes to 1. And what do we say then if our left does this limit exist? Sorry. So, and the limit exists, right? So the limit going towards our area has to be what? 1. Is that indeed the area for this shape? Yeah. So the limit gives you the area you're supposed to get anyway. Well, hopefully you understand that with this shape you could have just found the area by doing base times height times a half, because it's a triangle. But this whole process works for curves as well, and that's why, you know, it's out there. Okay, so you can apply this same process to areas underneath curves. Okay, so that's basically it. We're not going to do the whole thing here, but just in terms of the area, how would you find the area here? Well, you take your subintervals, which in this case they're all worth what? This base is 1, and then you multiply by the function at 1, and then you do 1 times the function at 2, plus 1 times the function at 3, plus 1 times the function at 4. That would be my left estimate. Okay, and on the right you would just scoot this over 1. Okay. If you're on this one, 8 subintervals, each length is a half. Well, basically you're just replacing this with a bunch of halves. So that's a half. We're still on the left, so it's a half times f of 1, because we are starting there. But then the next one would be at f1.5. And then it just repeats until you end up with a half times the estimate at 4. So it just becomes more, you know, it becomes more exact, more precise, but it's just more work at that point. Okay, then this over here basically is trying to show you what I was referring to a moment ago. That would be, you divide it up into intervals, and you keep adding them up, and you keep making them smaller and smaller and smaller. Okay, so this picture translates into that notation. So we go from a1 to a to the nth. So I'm over here now. So this is this first area, this is your last area, so that's how many intervals you have. Then you take the function at your first spot, so that is f1, whether it's a 1 or not. It could be, you know, starting from 5 to 10, it would be the function value at 5, with your first u being at 5. And then what does delta x represent? It's the length of each subinterval, right? Which is found by taking your first and your last. So let's say I'm going from 5 to 10 on my x-axis. You just do 10 minus 5, which is 5. And then you decide on how many intervals you want. Well, how many intervals do I want? Well, for this one I want 100. So the change in x would be 0.02 for this, for each of them. What does this symbol mean? Does Does anybody remember that from last year? Does anybody remember what it stands for? That's our sigma symbol, with the S standing for the sum of. This symbol here prevents me from having to write all this out. Okay, this really does say, starting with your first, I is 1, so I is 1 means start with your first interval, start with your first interval. Find what it is, find the area, so multiply delta x, which is your subinterval width or length, multiply that by the function at that first point, so this is your first point, and then what do? Well, add 1, then go with your second point, and do that again, and add it to it, so you don't have to write this mess out. So the sigma is just telling you, hey, keep doing this over and over. Okay, that would be your best estimate. Yeah, under one condition. Sort of a minor condition here, but what's the one condition? What has to happen to, if you compare your limit for your left interval to your limit on your right interval, what has to happen? Don't have to average them. What has to happen for you to use a limit at a point? The left limit has to be what to the right limit? Not less than. Don't they have to be the same to say that this limit overall exists? Yeah? Keep in mind, we started with that, and I snuck it in over here somewhere. Maybe I did it on the board. Can't remember. Maybe I didn't go far enough. There it is. The left interval was 1, the right interval was 1, so the limit for the area is going to be 1. Okay? That's one condition that you do have, so I'm scooting all the way over here. So that is this sentence over here. This sentence over here says, hey, you can do this, you can find this area by doing this over and over and over if the limit exists. Now, you know math teachers are notoriously lazy, so because this is such a common application, they did this one step worse. So if this wasn't short enough, what did we replace this with? That's that symbol. That symbol stands for a limit. It's the limit starting at point A going to point B of the area by dividing it into an infinite number of subintervals, multiplying by the base, and adding all the areas together. That's how lazy math teachers are. So they came up with this other notation there. And you can read that instead of having to say, you know, start at A, go to B, plug it all in, multiply. You can just say it's the integral from A to B of the function. That saves us a ton of time. Give you one example of that. Okay, this would be something I could put on your test. Find the area of the function square root of x plus 5 from 2 to 5. But now you've seen this nice new notation. I could also write it this way. Starting from 2, going to 5, use this function, and evaluate it as you continually make delta x smaller and smaller and smaller. That's that d of x. That's what it stands for. Okay, so it's mostly notation.